Okay, so I'm going to do a couple problems about percent composition in this video. As you can see, I have the formula for calcium chloride written out, and I have the masses of calcium and chlorine also. To do a percent composition calculation, usually what we do is we take the total mass, the molar mass of the molecule, so the molar mass of the molecule, and we put that on the bottom of a division. And on top, we take the number of atoms that we're wanting to know the percent composition of times the mass of that percent, or sorry, of that atom. So here, if we wanted to know the chlorine, like the percent composition of chlorine, we'd have to find the molar mass of the total molecule, and then we'd have to take the fact that there are two chlorine atoms in this molecule, and we'd multiply that number by our mass, so 35.45. This is the general way that we do things, and I think you'll see it as we go along. Hopefully you'll pick it up pretty quickly. But let's go ahead and get started on this. So the first thing that we have to do is calculate the molar mass of calcium chloride. I can see here from the formula that there are 1 calcium atoms, and that calcium atom will weigh 40.08. And we are going to also add the 2, because there are 2 chlorine atoms in the molecule, and each atom weighs 35.45, so that the total mass of this molecule is now the mass of the 1 calcium plus the 2 chlorines. When I plug this into a computer or a calculator, I get 110.98, and this will be grams. So basically what we're saying is that we have this many grams of calcium and this many grams of chlorine, and together they make 110.98 grams of this calcium chloride, which is actually the molar mass. So the molar mass is that 110.98 grams per mole, and we are going to assume that we have 1 mole of this substance, and so therefore we have 110.98 grams. Now, let's go ahead, I'll write out that little thing that I had. So we take our number of atoms, and we multiply that by the mass of the atom, and we divide by the molar mass. So if I wanted to do that with calcium, I know that there is 1 calcium. The mass of that calcium is 40.08 grams. That's a kind of a bad G. Let me redo that. And on the bottom, I put my total molar mass, which was that 110.98 grams that I found. And then, like I was saying in class, if we have grams divided by grams, that's something divided by itself, and it cancels. So the grams go away. But to make this into a percentage, we have to multiply this by 100%. Now, in your calculator, you might have a percent button somewhere, but don't actually use it. Just do this division and then multiply by 100. And when you write your answer, then just write a percent symbol. You don't have to plug anything into your calculator to make that happen. So again, just take the mass of the atom divided by the mass of the total molecule and multiply it by just the 100. And when you write your answer, then you can include a percent sign. When I plug this into a calculator, I get a total percentage of 36.1%. That is, the calcium atom will make up 36.1% of this mass of the total molecule. Also, let's say that I want to find my chlorine's contribution to the mass. So for chlorine, like you saw when I started this video, we'll take 2 chlorines times the mass of chlorine, which is 35.45, and we divide that by the total mass of the molecule, 110.98 grams. And this is 35.45 grams. Again, our grams cancel, and then we multiply by 100%, and the answer we get is about 63.9%. If I add these two numbers together here, 36.1 and 63.9, the answer I get is 100. And 100%, that's what we'd expect, because if we take the total mass of all of the chlorines and we add that to the total mass of the calcium, we'll also get the 100%. We'll get all of the mass of that molecule. Here I have sodium bromide, and I also have the masses of sodium at 22.99 and of bromine at 79.99. So my molar mass, which is the first thing I need to calculate when I do a percent composition, is 22.99. Of course, there are 1 sodium in this molecule. And we will add to that the contribution from bromine, which is 1 atom times 79.90. This is going to be the same thing as just straight away adding 79.9 to 22.99. So if you want to do that, that won't make it much of a difference. Mathematically, it won't change anything. It's just sometimes we like to do things in a very careful and procedural way. And so we put our ones out in front just so that we kind of reinforce this idea that's 1 atom in this molecule. So if I want to calculate my percent composition for sodium, I would take my number of sodium molecules, which is, or atoms, number of sodium atoms in the molecule, that is 1, and multiply it by the mass of 22.99 grams, and then divide that by the total molar mass, which, I forgot to calculate that. If I add these two numbers together, I get a molar mass of 102.89. Now to calculate my sodium's contribution, I just divide it by that 102.89 grams, and I multiply by 100%, and my answer is somewhere around 22.3%. Just to be thorough, let's go ahead and do bromine. So bromine, there is 1 atom of bromine in the molecule, and the atom has that bromine has a mass of 79.90 grams. And we divide that by the molar mass of the total molecule, 102.89 grams, and grams cancel, and we multiply by 100%. Also, grams cancel here as well. If I were to do that, I get 77.7%. And when we do percents, you only need to have 1 decimal place after your percent. You don't need to do 2 or more. Just do 1. That's enough, I think. Okay, so now we have magnesium. I believe this is magnesium perchlorate. To find the molar mass of that, I will take the number of magnesiums, that is 1, and I will multiply that by the mass of the magnesium, 24.31 grams. I will add the total number of chlorines. Now, this is where it gets kind of weird because we have a polyatomic ion here. You can tell it's a polyatomic ion because there are these parentheses that are around it. And when we have polyatomic ions with parentheses around them, we take this number outside of the parentheses and we multiply it down below. And here for ClO or perchlorate, it's like there's 1 chlorine, and so there should be an imaginary 1. And when you multiply 2 to 1, you get that there are 2 chlorines. So I take 2 times 24.31 and grams. And the same thing happens with the oxygen. There's an imaginary 1 there that we just don't put there. The oxygen there is enough to say it's just 1. And so I'd multiply my 2 into my oxygens, and I get 2 times 16.00 grams. If I add all of that together, what do I get? I get 127.21 grams. Now for the percent composition of magnesium, I would do the number of magnesiums, that's 1 in the molecule, so there's only 1 magnesium up here, and I multiply that by my mass, so 24.31 grams. I divide everything by my molar mass of the total molecule, the 127.21 grams. Grams cancel, and I also multiply by 100 to get my percentage, and I get something 19.1. For chlorine, we have 2 chlorine atoms because there's that 2 outside of the polyatomic parentheses. So I take 2 times the mass of chlorine, 35.45 grams, and divide by the molar mass of 127.21 grams. The grams cancel, and I need to also multiply by 100. Now, the answer I get for that is 55%. 55.7%. And one more atom there, that's the oxygen. And we would take the number of oxygens, which is 2. There are 2 oxygens in the magnesium perchlorate. And I multiply that by the mass of oxygen, 16 grams, and divide by 127.21 grams. That is, again, the molar mass. And multiply by 100, of course. The answer I get is 25.2%. Now, if I added all of these numbers together, I don't think I will get 100%. Let's see, we get 75, 89. These two added together give me 80.9%. And then if I add this one together, oh, very nice, actually, it does add up to 100%. But the point I'm trying to make is that sometimes, especially when you have 3 or more different atoms in your molecule, there's a chance that your total percentages might not add up to be 100%. And that's okay as long as it gets really close. So if you get 99.7%, that's fine. If you get 100.3%, that's also fine. That's just a rounding error that happens when you do division. It's unavoidable, but as long as you're not at like 120% or 35% when you add up all of your masses, then, if you're way too high or way too low, that will be an issue. So make sure that it's close to 100% when you add them together. All right, so this is lithium sulfite, Li2SO3. Again, we have another polyatomic. Here we have the parentheses. This 3 is on the oxygen, not on the whole polyatomic ion. So there is only 1 sulfur in this total molecule, and there are 3 oxygens in this molecule. If it were like SO and there were 3 sulfurs and 3 oxygens, it would be written like this. But because the 3 is inside the parentheses next to the oxygen, it means there are 3 oxygens and only 1 sulfur. So first thing I do, of course, is calculate my molar mass. I know there are 2 lithiums, and I take 2, let's put that up a little bit. I take 2 times the mass of lithium, 6.94 grams. I add to that the sulfur. There's only 1 of those, and it weighs 32.06 grams. And I also do my oxygen. There are 3 oxygen atoms, and each one weighs 16.00 grams. Well, actually, they're AMUs. There are 3 oxygens in this molecule, and they make 16 grams total. So if I add all these things together, I get 93.94 grams. That is, 1 mole of this lithium sulfite will weigh 93.4 grams. 3 times 16 grams of that will be oxygen. 1 times 32.06 grams of this 93.94. So this many grams will be sulfur, and 2 times 9.6 or 6.94 grams, that many grams, roughly 12, 13 grams, will be lithium. So to calculate my percent composition for lithium, I take the number of lithium atoms, that is 2. I multiply it by the mass, 6.94 grams, and I divide that by 93.94 grams. I forgot my grams up here. We'll put it up there in red. Multiply it by 100, and the answer is 14.8%. And that makes sense because even though there's 2 of them, these lithiums are very, very low in the periodic table, and so they're very, very light, and so they wouldn't really contribute much mass to a molecule. For sulfur, For sulfur, I have 1 sulfur. Its mass is 32.06, and if I divide that by the molar mass, 93.94, I forget my grams and grams. My grams will cancel. I need to multiply by 100%, and I get about 34.1% as my percent composition. And then we also have oxygen left over. So if I take the number of oxygen, which is 3, multiply it by the molar mass of 16.00, and I divide that, this is 16.00 grams, I divide that by the molar mass of 93.94 grams. Grams cancel, I multiply by 100, and I get about 51.1%. All right, so those are how we do percent composition calculations for molecules when they're given to us in this form. So this is our formula, but what if they're given to us in a different way? Here I have 3 problems that have a different way of telling you that this is a certain molecule. So I have this cobalt-3 carbonate. I need to figure out the molar mass of that, and to know the molar mass, I will need to know the formula for it. So the formula, again, will look something like this MgClO2, with just the atoms, the element symbols, and the number of atoms in each, the number of each atoms in the molecule. But here we don't have that. What we're given is cobalt. We're given that cobalt has a +3 charge, and it's also bonded to this carbonate. So carbonate is a polyatomic ion. We know that because there's a T here. Right? If this was carbonate or something like that, it wouldn't be a polyatomic because it would just be like a single thing, single atom, a single element. But here, since it's with an 8, we know that that's probably going to be a polyatomic ion because of that T. And so if we go to our list of polyatomics, we should see that it is CO3 -2. I'm going to write cobalt, which is CO, and I'm going to give it its +3 charge. And then I'm going to write the polyatomic carbonate, so CO3 -2. If you remember from last semester, we did a little procedure to figure out what our formula was. We would take this number here, we'd ignore the negative sign, but we take this number and we put it down here where the cobalt goes, or next to the cobalt. And then we will take the number above the cobalt and move it down here to the outside of this CO3. And so the formula unit that I get when I do that is CO and then 2, and then parentheses, because whenever we do a polyatomic ion, we always put it in these parentheses. So parentheses, CO3, and then 3. So I know that there are 2 cobalts in this atom. I know that there are 3 times 1 carbons in this atom, and I know that there are 3 times 3 oxygens in this atom. So to find the molar mass, I will take the number of cobalts, which is 2, multiply it by the mass of cobalt, 58.93 grams. I will add the number of carbons, which is 3 times 1, or 3. So I take the number of carbons and I multiply that to the mass of carbons, 12.01. And then I add to all of that the number of oxygens, which here is 3 times 3, or 9, times the mass of 16. And these are all grams. So the answer I get when I add and multiply all this stuff together is that my cobalt-2 carbonate should have a total mass of about 297.89 grams. So 1 mole of cobalt-3 carbonate will weigh 297.89 grams. The cobalt, since there are 2 of them, and I want to calculate the percent composition, I write my 2 times the mass of cobalt, 58.93, and I divide by the total mass of the molecule, 297.89 in our grams. We need to remember our units. Our units will cancel, and then I multiply by 100% to get my answer, and I get 39.6%. For carbon, do the percent composition of that. We know that there are 3 carbons, So if I take 3 times the mass of carbon, 12.01 grams, and divide that by the molar mass of 297.89 grams. Also, we multiply by 100. Grams cancel, and I get 12.1%. Finally, to do the oxygen, we know that there are 9 oxygens because it is 3 times 3 oxygens. 9 oxygens, and each one weighs 16. And I divide that by our molar mass of 297.89. And my units cancel, multiply by 100%, and my answer is 48.3%. So in this cobalt-3 carbonate, the cobalt will make up 39.6% of the mass, the carbon will make up 12.01, and the oxygen will make up 48.3% of the mass of this molecule. Another one, lead-4 hydroxide, so this will be similar, hydroxide. Now this is one of the few polyatomics that has an IDE in it. It's kind of a weird one because, well, really for historical reasons, but the important thing is that if we need to know that hydroxide is just this OH minus polyatomic ion. So it just has a single oxygen, a single hydrogen, and then we have our lead. So to calculate our molar mass, I take the number of leads, one of them, or actually, let's get our mass, or our formula first, sorry. So I know lead, Pb, and I know that it has a charge of 4, so it is positive 4. And then I know hydroxide has a charge of -1. So we do our little crisscross thing, take our 1 here, it goes down with the lead, and then on the lead we have a 4, and that 4 goes down to the hydroxide. So the formula that we get from this is Pb, and then we do parentheses because we protect our polyatomic ions in parentheses. So Pb, the polyatomic ion hydroxide, which is just OH, and then the number of hydroxides, or OHs, that is a total of 4. We had to do this because we need to balance the equation, and we need to make sure that our charges end up being neutral. So I have a positive 4 charge from lead, I have a -1 charge from hydroxide, there are 4 of them, so I have I have 4 negative charges, and I have the 4 positive charges from lead, and those cancel, and we are left with an overall neutral molecule. Then to calculate the molar mass, I take that there is 1 lead, and I multiply that to the molar mass of lead, 207.2 grams. I add the number of oxygens, which is 4 times 1, or 4. So 4 oxygens, each weighing 16 grams. And I add also the 4 hydrogens, one weighs 1.01. When I add all of this together, I get 275.24 grams. And then I can calculate the percent composition of lead. That would be taking the number of lead atoms in the molecule, 1, and multiplying that by the mass, 207.2 grams. Divide that by the molar mass of 275.24 grams, and then multiply by 100 to make it a percentage. I get that this is about 75.3%. So this lead-4 hydroxide, about 75% of it is the lead. There are 4 hydrogens because there are 4 hydroxide ions, and that means that we take our 4 and we multiply it into here, and 4 times 1 is 4. So I take 4 hydroxides times the mass of hydroxide, 1.01 grams, and I divide that by the molar mass of 275.24 grams. Grams cancel, I multiply by 100%, and I get somewhere around 1.5%. Again, that makes sense because hydrogen is just a proton. It's very, 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 very light. And so it, even tons of them only contribute a very small amount of the mass to a molecule in most cases. Last one we have is our oxygen once again. There are 4 oxygens, and so I take my number of oxygens, multiply it by the mass, 16 grams, and divide that by the 275.24 grams, our molar mass for the lead 4 hydroxide. I multiply all of that by 100 to make it into a percentage, and I get 23.3%. One final one, this is copper 2 iodide, and you might think, oh, now we have to do a polyatomic because it looks like kind of maybe it's a hydroxide, so maybe it's like an IO or something, or an IH, or who knows. Or maybe it's just like carbonate with the CO3 2-. But it turns out that because it has this D in it, this is just iodine. So copper, Cu, has a positive 2 charge, plus 2. Iodine, it has a negative 1 charge. And we know this because it's in the halogen section right next to our noble gases. We said the fluorine, chlorine, bromine, and iodine all have a -1 charge. And then we do our crisscrossing thing. So I take my 1 and it goes to my copper. I take my 2 from the copper and it goes down as a subscript for the iodine. And I now know that my chemical formula for this copper 2 iodine is CuI2. To get my molar mass, I take the number of coppers, which is just 1 copper, and multiply it by the mass of copper, 63, not 6.3, but 63.55 grams. That is my mass of copper, one of them times 63.55 grams. And I add 2 times my iodine, because there are 2 iodines. So 2 times the mass of iodine, 126.90 grams. And I plug this into my calculator. I get 317.35 grams. So that's my molar mass for my copper 2 iodide. To do the calculation for copper, or for the percent composition of copper, again, I take that there is 1 copper, I multiply it by the mass, 63.55 grams. I divide that by my molar mass of 317.35 grams. Multiply by 100%, or multiply by 100 to make it into a percent, and I get 20%. So 20% of the mass of this copper, or this copper 2 iodide, is just the copper. And that means that probably the remaining 80% is going to be iodine. But let's just go ahead and verify that. So I take my 2 iodines and I multiply it by 126.90. That's their mass. And I divide by the molar mass of 317.35 grams. Grams cancel. Multiply it by 100, and I get about 80%, 79.98, something like that. Close enough to 80%. So again, we get that full 100%. That is how we do a percent composition type of calculation. You will be asked to do several of these on the summative, and I hope this helps you figure out a good method for solving these problems for yourself.